Alright, let's see here. Choice 1, create a quadrilateral and label it ABCD. Construct midpoints, each sides EF, J, G, H. And create, joining consecutive parts, midpoints to create a new quadrilateral EFGH. Explore the sketch and create at least 3 different conjectures. Describe the different types of drafting strategies you use to develop each conjecture, and select one of the conjectures to create an impeccable justification using features of the dynamic geometry tool to provide a convincing argument. Okay, cool, no problem. Luckily in GeoGebra, I already had one made. Awesome. Perfect, still there. Okay, so moving these around, I'm sure I got it, because I'm right. E, F, G, H, A, B, C, D. Perfect. So yep, everything's labeled accordingly, and we can proceed moving these around. I just thought those in so it would be easier when I move this around, I don't feel get lost. Confusing. Okay, and I have the measurements of the outside of the larger ABCD. Okay, yeah, ABCD square or quadrilateral on the outside, and the measurements of each side of quadrilateral EFGH on the inside here. So the outside quadrilateral has a measurement of 6 on each side, and the inside has a measurement of 5 on the inside. It seems like the measurement of the inside, at least the length of the sides, will always be 1 less than the measurement of the outside. Let's see if that's true. Ah, I hear you. Okay, so nothing. So here the outside is 7, but the inside is 5. Okay, so maybe that conjecture is a good guess. Because that doesn't really work. He's dragging me along now. Oh, interesting. It doesn't seem to be proportional. The changes in measurement compared to the of the inside compared to the measurements of the outside quadrilateral. Huh. Well, this is a perfect square, and these are the midpoints, right? Yeah, those are midpoints. All these are the midpoints. Interesting. But I wanted to take it that there's similar triangles. Sorry, not similar triangles. Similar squares, though, because they both share 90 degrees. Wait, let's make sure and check that right here. Hold on. Here we are. Let's measure these angles. First off, I want to measure D, C, B. Okay, that's a right triangle. I'm sorry, a right angle. Alright, now let's do the inside. Oh, I need to make sure this side is right. Oops, on the side, another line. What to do here? Okay, yeah. So that's a right angle too. Let's try the inside of this quadrilateral. Okay, so that's 90 degrees. But here. Oops, never mind. Let's try this one. See if we can move that. And yeah, that's 90 degrees. Okay, cool. See how they're both 90 degrees. Both of the shapes are constructed, and they all have 90-degree angles on each of these points. So these two are 90-degree angles, and these two have to be 90 degrees as well. Because of the sides are all the same, so that means the measurement of the angles have to be the same in this instance. The same thing here. Okay, cool. So they're similar triangles, but I can go into another piece of that. What's another conjecture? Well, if I were to take the centroid, I know how to take the centroid of a triangle. That's with taking the angle bisector of each corner here, or of each angle, the angle bisector. So, what if they have the same centroid? That might be something. Wait, let's check here. Angle bisector. Take the angle bisector. Oh, excuse me. Alright, let's take it here. Angle bisector. Okay. That was a good thing, wasn't it? Whoops. Let's do that again. Take the angle bisector of the move of B. Alright. And because there's the outside ABCD is a perfect square, I don't need to take the angle bisectors of the other ones. Not necessarily. I can, but they'll just overlap the lines that have already been made. Interesting. So this point right here should be the centroid of quadrilateral ABCD. What about the centroid for EFGH? Alright, how do they angle bisector of that too? So let's do that. Boom, boom. Boom. Okay, okay. That does it. Let's see if another does. Boom. I'm going to start there. I'll start here. E, H, U. Ooh, interesting. Okay. Okay. So it does look like they share the same point M. And maybe the midpoint or centroid. Okay, so quadrilateral ABCD and quadrilateral EFGH share the same centroid. And that makes sense. That makes sense. Because if the inscribed quadrilateral is made through the midpoints of the exterior quadrilateral, then they should have the same center of gravity. Right here. What else? Huh. Looking at the angle bisector, it seems as though this right here, the angle bisector of the exterior quadrilateral runs through the midpoint of the inscribed line segments of the midpoint quadrilateral. Huh. Let's take the midpoint. Let's see if that's true. Take the midpoint of, say, line segment EH. Huh. Seems like it does. Let's see if it does it work here. Work on all of them? Nice. Seems like it does. Okay, so I think the conjecture I really want to prove is let's see, which conjecture did I make? So I made the similar squares, yes. That the two quadrilaterals share the same centroid, if they do. And my last one, the midpoint of the inscribed square lies on the perpendicular bisector. I think the centroid might be more interesting to prove. So I'll go for that. So, proving that they all, both quadrilateral ABCD and EFGH share the same centroid. The reason being, we know that quadrilateral EFGH was created through the midpoint of quadrilateral ABCD. So that automatically shows how they have similarity, and they all have right angles at every angle. So if that were the case, the midpoint of each line segment or each side would have to be along the line of the centroid. So it will have to be along the lines of the angle bisector of angles A, B, C, and D. So the midpoints here would have to lie on that angle bisector. And I know to find a centroid would to take the angle bisector of each angle. So yeah, that would prove that both of these shapes have the same centroid, or have the same center of gravity. Okay, interesting. I hope I got everything. So like one of the injection cave justification. Okay, yeah. Hopefully that's justification enough that they share the same centroid.